Hello. So I'd like to talk about topological solitons, bringing life to topological structures like charges, like here, vortices, and knots. So as it is the main motivation here will be the reparation of Gauss law that in nature it returns a charge being an integer number, while the naive Gauss law returns a charge being a real number. So we can repair it by using this topological vortex, which is so its topological charge is calculated by curvature like here. Yeah, so integrating this curvature, we will get the topological charge, the Winning number for so how many times the sphere wraps around if you go around. So there is topological Gauss law called Gauss-Bonnet theorem, and if we interpret this curvature literally as electric field, then our Gauss law will count the topological charge, so we will get the missing charge quantization. Yeah, so this is the first motivation here to try to repair the Gauss law. So generally, finally, we would like to understand the particle physics. So if we, so here is a standard algebra, apple plus apple equals 2 apples, but this is only approximation. So we can ask further questions. What is the structure of this apple? And similarly for physics. So there is usually use this perturbative approximation in this Feynman diagram, but we should be able to ask what is the field configuration hidden, represented by this Feynman diagram. So yes, so like here. And indeed, using these topological vortices, we'll get Coulomb interaction, and we also discuss further particles. Yeah, so I start with one-dimensional solitons, like here, then also two-dimensional, three-dimensional, getting this Coulomb interaction, electromagnetism, and further, finally, adding also twist of this vector field like here. Yeah, so going from start recognizing the twist, and this twist will also will have much lower energy corresponding to quantum mechanics, quantum phase evolution. Okay. So we have the topological defects, the basic one. So in one dimension, we can have this change of domains, also in two dimensions. But in two dimensions also appear the vortices. Yeah. So in three dimensions, we have all three. We have the domains, we have vortices, and we have the point-like defects. So regarding the domains, so if we use this liquid crystal-like field like here, then there are no domains, because this particle, this ellipse rotated by pi, is the same ellipse. So we don't need the domains, and in particle physics, I don't know any suggestions for domains. So generally, we don't need them, and we can avoid them by using this kind of field like this ellipse-like field, which also allows for 1/2 topological charge like here. So, but we need these two. We need both the vortices and point-like charges. As mentioned, for point-like charges, we will get Coulomb interaction. So we will derive as effective Coulomb potential. For Lorentz invariance, we get anti-electromagnetism. And now the vortices. So the vortices, turns out, they are required for quark strings. That between quark and anti-quark, there is this one-dimensional structure called quark strings, gluon flux tubes, and it has linear energy per length. So to understand quarks, which are kind of against the charge quantization, we need both. We need both the vortices and the electric charges. And here is such view that we have this topological vortex as quark string, and we add this fractional topological charge as quark here and here. But we can do it, but there is some problem. So we perform fractional rotation, but there is a problem. There is a conflict between them, and this conflict which will have linear energy per length. So this way we get this corner potential, that we have the Coulomb interaction, then linear dependence between them. So these quark strings also are used in so-called string hadronization. So they believe that for example, in LHC collisions, there is created this quark string, and it decays into particles. So finally, to understand which particles should correspond to which topological defects, we just need to find the correspondence, what they observe in LHC collisions, and what the topological vortex can decay into. Yeah. So and this basically the topological vortex and this point-like charges. And as I will try to convince you that they are sufficient, that we can recreate the particle physics with these two basic topological vortices, most of particle physics. Okay, so this recent Nobel Prize was given by very similar topics that such looking macroscopic object topological vortice charges are still agree with quantum mechanics. So quantum mechanics is not just some microscopic, but we can also understand it for larger objects like these topological charges, or maybe more specifically. So there are here are some three articles for interference, observing for fluxons, these topological defects, tunneling, so like in Nobel Prize, but more recent, for fluxons, and a Harnov-Bohm. Yeah, so for these topological solitons objects, there are recreated quantum-like phenomena. I also recommend these very nice walking droplets experiments with these articles. So they are using this kind of shaker. There is a bath with some fluid which is shaked, and having a droplet which bounces for a long time and creates waves, interacting with these waves, these pilot waves. They recreate interference pattern, for example, the double slit experiment. So here is statistic for double slit experiment. Then some trajectories that the droplet goes one trajectory, but its couplet wave goes all the trajectories, piloting the wave. They get tunneling, that this couplet waves has practically random behavior, so getting the probability of crossing a barrier. Then they get orbit quantization, like here, that this couplet wave has to become standing wave, so getting the like in stationary Schrödinger equation. Yeah, so this couplet wave is basically described by Schrödinger equation. So with these classical wave-particle duality objects, indeed we can recreate quantum mechanics. So we should. This is working on these topological defects. Still, quantum mechanics should be reachable by this kind of, especially this kind of behavior. I will also discuss further. Okay, so let's go to topological defects. The simplest one are the one sine-Gordon, which is just a lattice of pendula. Like here, it can be realized with this lattice of pendula. We've connected with a spring. So this pendula would like to be go down. Yeah, here is down, but there is also another down. 2 pi farther, there is also another minimum of potential. So we have periodic potential, and there can be solution which goes from one vacuum to another vacuum. And now there is some hidden energy, there is some imprisoned energy, and it cannot to release it. We would need to meet it with opposite charge. So there is per creation, per annihilation. We have this resting particle, massive, which we can only approach the maximal velocity, the propagation velocity. And if we try to approaching, so here is standing, he's moving. Yeah, so we get exactly special relativity, as Lorentz contraction in time. Yeah, so this simple setting recreates many particle physics phenomena like percolation, quantization. There is only short-range interaction here, so I will also talk about long-range interactions. There can be massless and massive particles. Okay, so and there is also time dilation, that there is a breather. So there is this oscillating solution. Here is resting, and there is boosted. So now moving particle has a smaller number of ticks. Yeah, so we have a clock. If we boost it, also here, when they oscillate, then there is reduced number of ticks. There is literally time dilation if we use Lorentz invariant theorem. Okay, so now let's go to three dimensions. So generally we start with electromagnetism, which is very close to hydrodynamics. Yeah, if you think about hydrodynamics and electrodynamics, then there are very many articles showing that similarity. So here is a larger one. For full agreement, we should use zero viscosity. So for superfluid, So here is a simpler one, but basically the A field corresponds to velocity in this analogy. The B field corresponds to vorticity. And there is, for example, a Barnett effect that rotating even uncharged object, we create magnetic field. There is Lorentz force corresponds to Coriolis force. There are these kind of formulas for superfluid connecting all three: A field, momentum, and this derivative gradient of phase. For these walking droplets I have mentioned, they get Zeeman effect. Yeah, so here is the Zeeman effect that they rotate. They use two droplets and rotate this fluid tank. So if they rotate in the same direction, you will increase the radius. If the opposite, you will decrease it. Here we can see that literally the Zeeman effect using Coriolis force as Lorentz force because of this analogy. Yeah, so they can recreate many effects this way. There's also a Haranov-Bohm effect. I think it probably started this similarity by Michael Berry. Okay, so here is this analogy, but what we are missing is the charges, point-like defects being charges. Yeah, so the question how to add a charge, quantized charge here, and it is done experimentally in liquid crystals. That we have this now we have this vector field, practically this field of this let's say this ellipse-like objects, and they can create a positive topological charge, negative topological charge. And for example, looking at the distance versus time, they can get this kind of dependence. So it means long-range interaction. We can fit some polynomial and can check. And there are many articles of this type, getting different types of these long-range interactions. So we would like to get exactly Coulomb interaction for Lorentz invariant theory to get electromagnetism for such quantized charges as topological. And let's think how to get exactly electromagnetism. We have a Gauss law, which looks like here. Yeah. So we have the charge is integral over some surface of electric field. And there are these topological versions with topological charges where the topological charge is this number of winding number. Yeah, so this how many times we wrap sphere around sphere. So to calculate it, we need to integrate Jacobian, and Jacobian turns out to be this curvature. So we get this Gauss-Bonnet theorem that looks very similar as the Gauss law, but using the curvature in place of electric field. So we should just take some deeper field, define its curvature as electric field, and now our Gauss law we return integer topological charge. So we have repaired the lack of charge quantization in the Gauss law. Yeah, so here this is approached by Manfred Faber. So we have some, let's say, field of unitary vector Sn. We define its connection. It's close to A field. Then its curvature is this one. So it's formally dual curvature, and we use standard electromagnetic Lagrangian for F as this F tensor. So it's formally it's dual F. If you use the original, you would get the magnetic monopoles, but just renaming them as using dual formulation, switching electric and magnetic field, we can call them electric monopoles instead. So in nature, we observe only electric monopoles quantized, not magnetic. If you use this dual formulation, we get as in nature, only electric, not magnetic. Yeah, so here we can see visually that the farther these two opposite charges are topological, then the higher energy. Yeah, so this way we get effectively interaction that we see in the moment that we get Coulomb interaction. We can also think about virtual particles. How can we think about virtual particles? So imagine that we start this process but lack energy. You cannot finish this process because of not having enough energy. Yeah, so we have smaller energy. So we just go here and go back. Yeah, so it will be kind of field perturbation toward pair creation. Yeah, so in the Feynman diagram it would be this virtual particle, but we can also understand it by this field dynamics, because the virtual particles are in fact in this perturbative approximation, so they should correspond to some concrete field configuration dynamics. Okay, so here is a simplified calculation of this effective Coulomb potential. So we place two topological charges in various distances. So here are the opposite, here are the same. And we calculate energy of this configuration by integrating this Hamiltonian. I have mentioned this sum of square of curvatures. Yeah, so we use curvature as F tensor to make Gauss-Lorentz topological charge for charge quantization. Yeah, so here we put this in this Hamiltonian, integrated, make a hole inside the singularities. I will talk later about this regularization of singularities. And now we get the points. Yes, and the points we can see agree well with one over distance potential, so we effectively get Coulomb potential. Yeah, so this is simplified calculation. I will talk further. So yes, one problem is that it makes the hole in the singularities. We regularize in a moment. The second is we should minimize this field configuration further. But so the more appropriate calculations were made by Faber, getting this kind of plot. So okay, so now let me talk briefly about this regularization. So we had this field of unitary vectors, but if you think about the center of such a hedgehog of this topological charge, we would get infinite energy usually. So the question is how to repair this discontinuity in the center, which leads to infinite energy. And the standard way in soliton models is the Higgs potential, Higgs-like potential. Yes, so that we like here, this Higgs potential, it prefers unitary vectors, but allows them to deform. Yeah, so in the center it deforms to vector equals 0, but it prefers unitary vectors, but in the center allows them to deform. If we wouldn't allow for that, we'll get infinite energy. Yeah, so we need this kind of Higgs potential not to get infinite energy of charge. So explain why electron has finite energy. Yeah, so this is standard approach. And so now this problem of this infinite energy of charge is well known. So if we integrate this energy of electric field alone, like here, if we integrate it from 0, we get infinite. If we integrate it from 1, approximately 4 femtometers, we can get the mass of electron. Yeah, so we just get the entire mass of electron by this if cutting the sphere inside. So we need a deformation in distance like a few femtometer, not to exceed the mass of electron with energy of its electric field alone. So if we do it with this Higgs-like potential, so Martin Faber has calculated getting this kind of plot. Yeah, so what we can see, this is very small distance, like femtometers, and we can see that the Coulomb becomes slightly stronger. Yeah, so the Coulomb interaction becomes stronger, what is well known as the running coupling effect, that the alpha deciding running the Coulomb interaction becomes stronger for very high energy, means very low distance. So Martin Faber has shown that indeed this effect, this regularization of infinity to finite the energy leads to the running coupling effect. So we get agreement with the running coupling. So we can very briefly talk about the arguments for the electrons being perfect point. So yes, people say that, but if you look at the arguments, usually there is cited this Delmetz 1988 article, which has this plot that we have triton as made of three nucleons, proton as made of three quarks, versus electron for hypothesis of being made of three partons. So Delmetz has probably started with a straight line through these 2 points, but he will get negative. So here is G factor, he's reduced. So if you use straight line, you would get negative. So what he did, it looks like he used parabola to extrapolate from 2 points. Yeah, so we cannot do it. We cannot extrapolate from 2 points with parabola. We can get any value we want this way. So this is a nonsense argument, but everybody uses it. So I recommend looking at that. So let's think about more serious arguments. So there is this electron-positron cross-section. So here is the plot, the cross-section for very high energies. This is 1 10 GeVs. So what we can see that in log-log plot, we get a line here plus some resonances for particles. Yeah. But the question is which cross-section should we use? So we are interested in resting particles. So we should take this line and extrapolate it to resting electron plus positron. If we do it, we get approximately 100 millibarns, what corresponds to 2 femtometers. So again, we get this distance, this radius required to deform from perfect point charge not to exceed 511 mass of electrons. So if we just using perfect point charges, we would probably get this kind of plot, but to but if you do it right, then indeed we electrons is not perfect point charge. Is we need some regularization just not to exceed its mass with electric field alone. Yes, so this is crucial that we need this regularization. Okay, and finally, this running coupling is another argument that if using perfect point charges, we wouldn't need any running coupling. Yes, we should just work. Okay, so let's go to further topological charge defects. These vortices. Yes, there are these nearly unavoidable these fluxons are because of vortex. So also in quark gluon plasma is called as perfect fluid, the most vertical fluid. And as mentioned previously, there are for quarks, quark anti-quark, there is required some quark string, which if you ask what it is, what is the field configuration, what is non-perturbative picture, the only answer I have seen is as topological vortex. Yeah, so there is quark anti-quark. Between them, there is this increased energy. So thinking about this picture as previously, so we have this topological vortex, and we add the charges, topological charges, by this inward outward rotation. If you would rotate by pi, you would get a hedgehog. But if you do it by pi third, we get literally a fractional charge. Yeah, so we have violated the charge quantization, but there is a cost. There is some nasty conflict between them because of these fractional charges. So there is linear energy per length because by using these fractional charges. Yeah, so we get both the Coulomb interaction, but also this linear because of this conflict. They call it this corner potential. Yeah, so first Coulomb, then linear, and indeed we get it here. Yeah, so Coulomb by charges, linear by this conflict. So we can violate the charge quantization, however, at cost a very high cost. So in QCD, this is like 1 gigaelectronvolt per femtometer. And if we have this Gauss law, it cannot cut a singularity. So this is a singularity. So our Gauss law cannot cut here this problematic situation. If we don't do it, we get only integer topological charges as we should do. So generally this conflict. So we can bend the topological charge, but at cost, very high cost, 1 femtometer, indeed used for quarks. So there are some more arguments that there should be some these one-dimensional structures. For example, in Sans corona, they observe these one-dimensional structures shining, and they suggest they also might have some mechanisms to make them stable. So maybe there is also this topological vortices. And another argument is that there are these so-called halonuclei, that we have some nuclei like lithium-11, that there is a core like here, lithium-9, and two neutrons in very large distance, like 5 femtometers. But for this nuclear force, the minimum is like here, 0.8 femtometers. So the question is, what binds the two neutrons for a very long time, like hundreds of milliseconds, and in Borromean way? So they say that if we remove one neutron, the other would also go away, and there are need three body forces. Yes, so I think the only reasonable explanation, I haven't seen any besides effective models which say that we put it by hands, is that we should consider these one-dimensional quark strings as maybe topological vortices, which literally connect them. So this way we should think about nuclei as knots of topological vortices. Yeah, so doing so, uh, if there is some topological vortex going through them, effectively it would be required. It would require T-body forces, and it might be Borromean. It could be very stable. So I think essentially halonuclei are a clear argument that we shouldn't think about quark strings as only inside proton neutron, but also between them to help binding of nuclei. Okay, so here is some summary of the two types of topological charges. So there is this two-dimensional, like here, that going around by some rotation. The field makes +1 rotation. Here the field makes -1 rotation. Here the field makes +1 also. Here +2, and also as mentioned, there can be also 1/2 if going around the field makes 1/2 rotation, but after 1/2, if you use this ellipse field like in frequent in liquid crystals, we get 1/2 this spin. So people think there is some magic about spin 1/2, but no magic is needed. And this is in agreement with quantum rotation operator, that rotating spin s particles by theta angle, the quantum phase rotates by s times theta angle. Yeah, so this is exactly in agreement with this spin. So we should think about this two-dimensional, this cross-section topological charge as spin, and this three-dimensional for Coulomb interaction as electric charge, quantized. Okay, so for electron is much more complicated than just topological charge. The just electric charge has both electric charge, but also magnetic dipole moment, also angular momentum. So there is something rotating, but it's not point. Yeah, so cannot think that electron is spinning point. Instead, these are field theories. So where is this angular momentum? Is the field. So it is field rotating, not the point. And also, as mentioned, these AB fields also require some field rotation. So I think this is the same. And moreover, there is also the clock of electron. It's called the Broglie clock, Bewegung. So that with this Schrödinger equation, we need to use energy as mc squared. Yeah. So literally, the mass of electron propels its clock. So the question is, from one side, here is a direct observation. I know one such article. So they used ATMF electrons shooting into silicon crystal. Thanks to that, the distance between the ticks of the clock agree with the lattice of the silicon crystal. If there is this resonance, then they get increased absorption, shown here. Yeah, so I think so. So we can say that it was directly confirmed. The question is, what is the mechanics? I will mention in a moment. So, but finally, I think that we should consider electron as something like this. That this is both this quantized electric charge, but also we need some angular momentum. Yeah, so the field is spinning, and also this gives the clock, also gives the magnetic field. So electron, I think electron is something like that it's not that topological charge, but it should constantly evolve like here. Okay, so having this clock of electrons, so as mentioned, we can get this, for example, these walking droplets like experiments with this shaker. So it uses external clock. For electron, it should be internal clock, again leading to this quantum-like phenomena, also including the double orbit quantization they get for these classical objects with wave-particle duality. Okay, so to briefly summarize the classical quantum, so people try to search for the difference, classical quantum world, but we shouldn't. I think we shouldn't. They are just different perspectives. So there is no classical quantum. If we have electron, proton, so what's happening when they meet and forming this? So let's think about these couplet oscillators. We can describe them classically, but we can also go to these normal modes, which becomes practically unitary evolution. So we get kind of quantum-like evolution. Then we can get a crystal as a lattice. So we can get classical description, but we can go to phonons, being again modes, and in quantum field theory described as real particles. Then the more difficult is the continuous limit, and as mentioned, they recreate you can get this quantized orbit for these walking droplets because of this couplet wave has to become standing wave. Finally, we need this multiple varying number of particles, and topological solitons also recreate them, and again can be described by quantum mechanics also. So this is just asking what is the description of given field configuration, and from the other side, what is the field corresponding to given Feynman diagram. So this topological approach for particles is also derived as so-called Skyrmion models. So they use very similar Lagrangian as I will show, but but they use potential with singular minimum. Yeah, so if you're using potential with singular minimum, then there are only short-range interactions, so they have only nuclei, and there are many problems with that, like what is the difference between proton and neutron. So instead, the main difference we use is that we interpret this topological charge as electric charge instead of baryon number. So I think it's much more appropriate, especially that this baryon number can be violated in theory by baryogenesis from radiation, but in this view it cannot be. So it can be ultimately conserved. Instead, only electric charge is ultimately conserved, we believe. So and calling it topological charge is yes, indeed, it will be ultimately conserved. So this is very similar. The similar kinetic term. I also will use this kind of term, with different interpretation, different potential. So they use this trivial potential. We use Higgs-like potential. So here is the Lagrangian. I think as very promising. So we have the standard looking electromagnetism, Young-Mills, Skyrmel potential. But this F, in fact, is a curvature of deeper field, like here. Yeah, so here we have this commutator. That means that we first go this way and then go this way and check what is the difference. So this is kind of curvature. Yeah, so curvature with weights, it's weighted curvature, we can say. So we interpret this weighted curvature as our F tensor and use standard electromagnetic Young-Mills Skyrmel Lagrangian. And there is this also this Higgs-like potential, which makes the vacuum non-trivial, like these unitary vectors. And finally, in liquid crystals, there is so-called Landau-Desjardins model I will use. So this Higgs-like potential, which will prefer some set of eigenvalues as our shape of the molecules. Yes, so like here that we have these three eigenvalues. So this Higgs potential, which prefer some diagonal of our. So we say that we have this field of M tensor, real symmetric tensor, and O is the local rotation rated also with boosts. If you go to 4 dimensions, and D is preferred by Higgs-like potential to have some fixed shape, and I use it like this. That we have that in space we have this one is for electromagnetism. This delta means that there is low contribution of quantum phase. So like in QED Lagrangian, we have both this electromagnetism, very high energy, and very low energy of quantum phase evolution. And finally, we have also this temporal axis, which will be much longer, and will correspond to gravity. It's small boosts. So why it should be much longer? Because creation of this hedgehog in space is electron is relatively cheap, but hedgehog of this long temporal axis would be a black hole. So it is much more costly. Yeah, so it should be much longer axis. Okay, so here is unification. So we use EB fields. We say that A is deeper because of, for example, of Aharonov-Bohm effect. However, those still allow for charge being a real number. To make charge on integer number, we need this even deeper field and interpret its curvature as its connection as A field, curvature as EB fields. So this deeper field kind of unifies these two types of rotations into these costly tilts for electromagnetism and cheap twists for quantum phase evolution. Yes, like in QED Lagrangian. So here is this F tensor finally written. So okay, I will discuss further and our electron. Okay, so finally in 4 dimensions we have both the rotations. Yeah, so as shown here we have this long axis. It can tilt. It's costly. It corresponds to electromagnetism, but there is also inexpensive twist, which, for example, in this QED Lagrangian corresponds to quantum phase evolution. So this twist can be thought of as quantum phase. And finally, we get this boost, which is much more costly, allowing us to unify all of them. So we will get also the second set of Maxwell equations for these boosts. So it's called gravity electromagnetism, and it's seen as approximation of general relativity confirmed by gravity probe. So we get this automatically. We get this unification, and there is also interaction between this electromagnetism and gravity-electromagnetism. For example, slowing down electromagnetic propagation in presence of gravitational field, what leads to line bending and time dilation. Generally, this approach is also called teleparallelism by Einstein. So we have field of four vectors which can rotate and boost. So to unify electromagnetism and gravity. So he tried to do it, but did not succeed. So I think the problem was that he used for the identical axis. But I think it's crucial that we say that this gravitation is much longer. Then we have this for electromagnetism. Again, so gravitation is much longer because Hedgehog of gravitational is black hole, and for the special is electron. So it should be much more difficult to create black hole than electron. Okay, so now regarding the clock for electron. So now we slide about a time model from this archive. So generally we have this phase evolution using energy as a mass of the particle. Yeah, so in field theory, the mass of the particle is integral of Hamiltonian. So we need a term in Hamiltonian which prefers some time evolution in presence of particle. And here is such Lorentz invariant clock, this curvature square as we discuss all the time. So like here, so we have this phi of this is spatial derivative of this field of the particle and temporal derivative of some quantum phase. Yeah, so having this negative term in Hamiltonian, indeed, in presence of particle, as this non-negative term, there appears a tendency for non-zero time derivative. Yes, and here we can see that such kink like here is its energy for resting, and by adding some rotation, it can slightly reduce its energy. Yeah, so so now we get the mechanism that resting electron neutrino can slightly reduce on energy by starting to rotate. Yeah, so what should its mechanism to propel the clock of the electron neutrino, for example. So that was the time model, and in the real model I'm using, like so as shown previously. So this is Lagrangian, but if we go from this Lagrangian to Hamiltonian, for two indexes we get only positive terms, but for four indexes there are also both positive and negative terms in our Hamiltonian. So here is again this F tensor, that here is this electromagnetic, quantum mechanics, gravity, but there are also these terms which have negative contribution in Hamiltonian. So yes, like here we get the negative contribution in Hamiltonian. What is crucial to clock propulsion, allowing to reduce slightly the mass of particle by activating rotations in the presence of particle. Yes, so there is automatically there appears a mechanism for clock of particles. Okay, so let's go to further particles. Yes, so we have now we have these three types of hedgehog: one hedgehog, second, and third. Because we live in three dimensions, so it looks like three leptons. So and we can ask why there are no naked charges. Because of I think because this Heiber theorem, if a hedgehog from one axis, second axis needs to perform some evolution. Okay, so so now let's think about the baryons. These topological vortices can also form a knot, like here. Yeah, so so here is one vortex and second vortex around. So let's think about this cross section of such a configuration. So we can see that the vortex around deforms the central vortex. And this deformation deforms toward the hedgehog. And hedgehog for us is electric charge. So a proton can just enclose this hedgehog. So we had here this is a proton-like configuration. But neutron also has this tendency and has to deform, has to compensate it. Yeah? So you have plus, minus, plus, minus, minus. So exactly like in the quark structure. Yeah, so we get indeed a quark structure of neutron because the baryon itself, due to this interaction, requires at some charge, and it needs to compensate it to zero. So we get these three quarks, yes, literally. So, and here are the quarks, six quarks. So three types of, because of we have three types of these topological vortices, and one third or minus one, plus minus one third plus two third, because the question is there is vortex around? If there is, there should be preferred two third. If there isn't, there is this minus one third. So finally, we get the six quarks. The W has reduced energy because of this agreeing with this charge enforced by this external vortex. And now we can also think about, as for neutrinos, so I will discuss further, but I think that the simplest vortex seems to be in agreement, again, three families. And we can now understand why it is easy to rotate between neutrinos, because we can just rotate the field. However, for protons, it's much more difficult because we have this knot, so it's much more difficult to rotate between quarks, much more easier to rotate between neutrinos because of this being just loop versus being a knot. So okay, so so here is some. The question is, what about the charge distribution? So for proton, it's indeed only positive, but slightly wider than for electron, the positron. For neutron, it is believed non-experimentally that indeed it's a positive core negative shell, as we have obtained. Yeah, so because of this, positive is required by this vortex around. So. Then for deuteron is also very interesting. So for us, deuteron will be like this: that we have two baryons requiring a charge. So we have plus plus, and there is some minus for compensation. So we can see this quite symmetric, and it's plus minus plus is electric quadrupole moment. And indeed, experimentally, the deuteron gets electric quadrupole moment. So, but it's very non-trivial. How to get with proton and neutron? How to get electric quadrupole moment? Yes, so here we get explanation, quite natural, by this preference of baryons to have a charge, and this is a start of this so-called EMC effect, that there is a problem with quarks for nuclei. So I mentioned in a moment. So that using larger nuclei, it does no longer work. Okay, so and I mentioned this halonuclei. So again, we need these knots. So I think it's crucial to include. I don't know how to understand without including these vortices. So we should think about nuclei rated as knots instead of those grapes of nucleons. Okay, so and now there is this mentioned string hadronization, so that they believe that in LHC collisions there is created this quark string and decays into particles, mostly pions, kaons, and some more natural. And so we need to find this correspondence, and I've mentioned that the simplex knots seem to be baryons, more complex as nuclei. Neutrinos very light and stable, oscillating, so seems close to similar to neutrinos. If we include twist of such loop, then it seems to be an agreement with strangeness. So these decays seem in agreement that we decay by one strangeness releasing pion, by two releasing kaon. Okay, so for neutrinos, so why we should think about neutrinos as this so one way to create neutrino is beta decay, that we have neutron, it decays into proton, and not only gamma photon but also neutrino. So that means that this energy difference between this neutron and proton has to go in some different way than just electromagnetic way. And this neutrino is very light and stable, so can get passed through air. So it's much more stable than photon. So we need some stabilization mechanisms, and this topological could allow for that. So, and we need some correspondence. It should correspond to some particle. So it seems in agreement. So you can also explain some different properties. Okay, so it's give some summary of some issues, problems that in fact so especially the EMC effect is the most important here. That trying to understand large nuclei through quarks, it doesn't work. Yeah, so it does work for single proton neutron, but if they do it, they get these dots. But I expected this line for EM. They don't understand it, and the simplest example is already the deuteron. So it's more complicated, and maybe this picture seems to provide some explanation. Here is some summary, and so organic applications. We could think about some proton decay. So in this kind of models, also in standard model, it's difficult to enforce that baryon number will be always conserved. So maybe we could think about trying to stimulate it. So if being able to stimulate proton decay, then we will get the ultimate energy source. But it's very difficult. But these models could allow us to search at least for that. So how to swing out this charge inside to make it go out from this ring outside. So we could think about some ways maybe to realize it, and maybe leading to some energy source. So here are these liquid crystal models. So there is this Austin Frank, Lano de Jean I have used. So here is some very briefly. So there is some derivation of Maxwell-like equation, also this Klein-Gordon-like equation on this quantum phase. So also some B spinor, so we can represent the particle. B spinor represents the boost and rotation. So we can also use it for this kind of configurations. And here is a similar derivation of Maxwell-like equation for gravity if we turn off the electromagnetism. And so here is some summary of this energy minimization, so various shapes of the particles. You can see the animations. And here is the last slide. So now we have this huge Lagrangian standard model, like 26 or more parameters, and it's obviously a perturbative approximation. It uses both the percreation, so it creates particles as just without explaining what field configuration is there. It uses probability distributions, again, which are effective, we should get from Feynman ensembles. So the question is where to search for a deeper non-perturbative model. So generally, it should be like something like that. So it has electromagnetic Yang-Mixer-like field. And this one is close to this Einstein teleparallel is just evolution of four axes. Seems to agree. So it gets electromagnetics, quantum mechanics, gravity electromagnetics, three leptons, neutrinos. So the topological defects also agree. So finally, we would like to show that the effectivity is described by this kind of Lagrangian. Thank you for attention.